Good morning, everyone. Welcome back at the online Power Electronics event. We continue with the third presentation of the day by 3T. Welcome, Jan Lenssen, and also Richard Meijer. Welcome. The presentation is about the surprising design choices for the powertrain of a world-class solar car. The presentation will take around 45 minutes. We do have also some interesting polls and open questions to you as viewer. Please fill in your questions already in the chat. And together at the end, Richard Meijer and Jan Lenssen will do a Q&A session together. Enough talking. I think let's start with the presentation. Jan, the screen is yours. Good luck with your presentation.
Thank you. All right, so hello everybody. My name is Jan Lenssen. I'm here from 3T. It's my pleasure today to tell you something about the surprising design choices for the powertrain of a world-class solar car. So this is the solar car of Solar Team Twente. Team that's also based in Enschede, also where 3T is. Short overview. So we'll start by explaining something about Solar Team Twente. I've also been a team member. I'm still very active there, and now with 3T as my employer, I'm also active from 3T. I will explain a bit about the powertrain of solar cars, and then go a bit more in depth in the Gallium-Nitride motor controller we helped design. And I also explain a bit more about the challenges we had with Gallium-Nitride. I know there are some more presentations about GaN, so we'll focus a bit on the parts I think that have not been explained by others. And in the end, I will show some results and also some insights we had. But I will start with Solar Team Twente. So this is a student team from the University of Twente and the Saxion. It's a team of a full-time team, so the students put their studies on hold for about 1.5 years. And they build solar cars for participation in the Bridgestone World Solar Challenge in Australia. So this is a race about 3,000 kilometers through Australia, from Darwin in the north to Adelaide in the south. And about 50 teams participate from around 30 countries. The solar cars are very efficient. They have to drive the whole stretch on solar energy, although they have a battery, so they can start with a fully charged battery. But the rest of the 3,000 kilometers is all on solar energy. So efficiency is very important for the team. The race is to get to the finish first, and the one that has the most efficient car will eventually get there first. So to give a bit of an overview, I have some pictures of which are borrowed from the team. This is their latest car. They're developing a new one for the next race. This was the one that participated in 2019. This is called Red E. During the race, there are a lot of several stops. The team has to switch drivers there and also gets a chance to charge the battery for 30 minutes while standing still. But you can see here it's quite competitive. The drivers run towards an actual physical button to get the timer to start. The race takes about 4 to 5 days. So yeah, it's a multiple day race, and the team finishes around 5 o'clock. They have to stop driving every day, and then they build up their camp, which you can see here. Sometimes that's at truck stops, so with some facilities like benches, but sometimes it's also in the middle of nowhere, and then they just camp out there where they stopped that day. So a first question for some interaction. I'm wondering whether anybody knows a bit more about the solar challenge, the solar cars in particular. Has anyone any guess about the top speed of a solar car? So I've talked a bit about the kind of race. So is that around 60 kilometers an hour? Can they reach even 100 kilometers an hour? Or is it only 30? So maybe they're not that fast at all. Or can they even reach up to 130 kilometers an hour? So there should be a poll on your screen, and then I will look at the answers. So the cars look very sleek. Just the question is, what's the actual top speed of such a car? Might be exaggerating here. Maybe they only go 30, and then it's a long drive. Maybe it's a bit faster.
I see that at least a majority of the voters think it's above 100.
Yeah. So yeah, for 3,000 kilometers and 5 days of racing, it should be fast, right? So we see that's about a third of the participants thinks it's about 100 kilometers an hour. Almost more than half thinks it's 130. Some think it's only 60, but it's in fact 130 kilometers an hour. So the speed is quite fast during the race. While it is the top speed, the cars do not go that fast during the race. The average speed is more around 90 to 100 kilometers an hour, because driving at 130 uses a lot more energy. But it's not unusual for solar cars to overtake tourists in Australia, which is quite a sight to see. So another question. At that top speed, so at 130 kilometers an hour, what is the required power of such a car? So I have some household appliances here as examples, and also an electric car. So we have the vacuum cleaner, about 1.5 kilowatts, an electric kettle of 2 kilowatts, an electric heater, which uses more around 3 kilowatts, and then quite an efficient electric vehicle actually uses somewhere in between of 8 and 15 kilowatts when driving outside of the city, but not at top speed. So what would the solar car use at top speed? So the electric vehicle is more in kind of a comparison, because if the electric vehicle is more efficient, then we would just stick solar cells on top of a normal vehicle. So the team spends a lot of time optimizing it aerodynamically.
And I think the viewers are tending more towards a higher power. So the 3 kilowatts is trailing at the moment.
Yeah.
But I think there's a surprising answer, but you can...
Yeah, the actual answer is more around 1.5 kilowatts. So quite low. You can see that you can drive around 130 kilometers an hour on that. As I said, it's not the actual average speed during the race, which also depends very much on the weather. So you need solar energy to drive, so the sun has to be out. But top speed can still be driven quite efficiently. But also sees what kind of steps we still can take with normal vehicles, because the 8 to 15 kilowatts is actually quite efficient for an electric car. So what's the relationship with 3T? So the solar team has been sponsored by 3T for quite a long time already. And a couple of years ago, the solar team came to 3T with a request for a new motor controller. So as you can imagine, even at 1.5 kilowatts, single-digit watts are very important. And the solar team already had their own custom-designed electric motor, but the motor controller was still off the shelf. And they wanted to go the next step and start working on a more efficient motor controller. So that was the main question: could that be realized? And of course, 3T thought that was possible, so we started working on that. But to explain more about the motor controller, you need to know a little bit more about the powertrain of a solar car. You can see on this picture is one of the rear wheels. And in one of these rear wheels is an electric motor, the one designed by the team itself, which is a direct drive in-wheel motor. It has permanent magnets and is controlled by field-oriented control, all to get the most efficient driving. In this picture, you see three devices, let's say. So it's the motor controller that converts the DC bus, which is about 100 to 150 volts, to the actual three-phase currents, which go through additional inductors and then go into the motor. And those additional inductors are because the motor is ironless. So it has a very high torque, but doesn't contain any iron. So it has a very low inductance itself, and not all motor controllers can handle that. So we need some additional filtering in order to control the motor optimally. And separate coils also permit faster revisions. And this is because we also found out that adding those coils is not necessarily bad, because you can also optimize that and create an even more efficient system if you pick the right parameters. So, and to understand that, we have to look at the energy losses in total. So of course, that's power out divided by power in. That's the efficiency of the system. There are many types of losses, and together with the solar team, we discovered there are quite a lot which you normally wouldn't really think about if you look at a normal motor system. Of course, one of the easy ones is resistive losses. So they're in all the three components: the copper losses, sending the current through those wires, but also in the motor controller itself. Of course, switching losses in the motor controller. Looking at the power electronics, I think that's clear for most people. We also have core losses, of course, in those inductors. So that's one of the negatives of using extra inductors. We might have eddy currents. So depending on the type of core in those coils, we could induce some eddy currents there. Small losses, but still there. And also in the motor, while not containing any cores for the inductance, there's still a lot of metal in there, so also eddy currents can exist in the motor itself. Maybe not really electronics related, but aerodynamic losses. So the solar team still has to take this into account, because one of the ways to optimize the motor would maybe be to add a lot more copper in parallel. So that would decrease the resistive losses. But what is the impact on the rest of the system? So the motor spins quite fast, has some aerodynamic losses, and if you do not take that into account, you might lose more on that trying to optimize the resistive losses. So we have to take it into account. Same is true for weight, still relevant for all three components. So everything has to be as light as possible, while adding extra weight might decrease some other losses. The motor is designed by the team itself. One of the things they have to be really aware of is current loops. So that's more of a production side of things. They do not want to have extra current running through the motor, which just heats up and does not contribute to the torque. Standby losses, even when freewheeling. So when not propelling the car, the motor controller still uses some energy, which of course has to be minimized. And we also have high frequency resistive losses, which is a number of different losses combined. All because we use switching elements at a higher frequency, and that can introduce losses in the multiple components as well. So the question really is, what's actually important? We focused on the motor controller, but we cannot neglect the rest of the components in the drivetrain. So it's really the system versus the individual components. If we started really optimizing the motor controller, we might not end up with a system that was more efficient at all. There's also a nice realization that you can sacrifice some things in certain places for the increase in performance. So things I already mentioned, and some things that might already be known to many people, is that you can increase the switching frequency, which would result in requiring smaller inductors. So they could have less resistance, so the total losses might go down. But the other way around might be true as well. Using bigger inductors, you might result to using lower switching frequencies. Maybe that's the optimum. And of course, weight is a very important one. We could decrease the resistive losses a lot, but we have to add a lot of material, which just increases the weight. And even though the cars are very lightweight, the last car was around 160 kilos, every kilo is still very important, because everything, it mostly introduces a lot of friction losses at the tires. So the new motor controller. As you can see here, this is a picture of the controller together with the car at one of the last races. Controller was based on the 3T fiber platform. We used it as a starting point, so that meant that we could really have the basis in place and really look at the things that we could use to optimize the system. One of the nice things of working with the solar team is that there were no limits in terms of material cost. Not entirely true, of course, but we only have a couple of devices in the end. So production costs, material costs are not that important, which really meant that we could do a performance study using the newest components and technology. Made it very interesting. And we also tried a lot and had a lot of nice ideas, which normally you would not follow up because of the costs. And in terms of the requirements, we were looking at a motor controller that could use up to 65 volts. And also could output 140 amps of current. So quick calculation shows that it's quite a lot of power. But the thing is that, when the car is driving normally, as you can see in the picture, it usually requires around 10 newton meters of torque to keep driving. So that's not a lot of power. But if at standstill, the car still has to go up a hill. And then you already use about 5 times as much torque, which is also translates to about 5 times the same current. So that's the main challenge in designing this controller. The actual nominal power is very low, but it should be able to deliver quite a lot of current. So the current system at Solar Team is already more than 96% efficient from battery to wheel. so from the storage to actually driving, and it's split over the motor controller, those coils, and the motor. So why did they want to improve the motor controller even more? So calculation might show why this is important to them. So what really is important is the effect over the long distance. The race is 3,022 kilometers long. So yeah, for example, driving that in 36 hours would require an average speed of 83.9 kilometers an hour. And going a single % faster, so 84.7 kilometers an hour, not that much faster, would already result in 19 minutes of gain during the race. So the team calls that race minutes. 19 race minutes has been gained. So they arrive at the finish 19 minutes earlier. Although driving at higher speeds, the losses increase substantially. That's not a linear, that's a more quadratic relation. So driving 1% faster requires a lot more efficiency increase, so more than 1%. So having told all that, can anyone guess how much faster the team will arrive at the finish when they use our optimized motor controller? So yeah, it's probably less than, it's about 4% that they can still gain. So it's around 96% efficient at the moment. So maybe you can do some quick calculations. Of course, you need to know the actual power loss driving at such high speeds. But still, I think the answer is quite interesting. I don't know if any answers have come in yet.
I don't see any answers on the chat. So if there is somebody who did the calculation quite fast, then I propose that they will send the answer through the chat, and we can check if you're right.
Some guesses are also all right. So it's is it in the order of seconds, maybe minutes, maybe even hours? So
I think everybody's still calculating, but maybe you can disclose the answer.
Yeah,
I get an answer from Bert van den Berg, 10 minutes.
Around 10 minutes. Well, it's actually quite close. So the actual answer is a secret, so the team doesn't allow me to share that. But some quick calculations show that's in the order of around 10 minutes, indeed. These pictures are not of the finish. They're one of the control stops after about 1,000 kilometers. And you already see, even though all cars stay there for only 30 minutes, they're all very close together. And one of the scoreboards show a difference between the number 1 and number 2 of 12 minutes, which actually decreased after that a bit. And there have been finishes of the race. So in Adelaide, after all those distances, which only had a couple of minutes between the competitors. So those race minutes are very important for the team, and that's all they focus on the whole year. So how did we try to realize that? So as I already told, it's based on the motor controller is based on gallium-nitride. This gave the best figure of merit for our application, and we saw the potential to reduce the system losses by about 50%. It's also a very interesting technology, still is being developed the last years, which we saw firsthand. There are some things available today which weren't when we started the development. So starting again, we would probably do some things differently, but it's still very interesting to be part of that development. So the challenges we saw with gallium nitride. I'm also interested, are there people in the public that have already designed something with GAN or even sold a product using gallium nitride? So we started doing designing with gallium nitride a couple of years ago. Have made some products, some systems. We have seen that there are a lot of challenges, but you also can realize some really nice things. And sometimes it's the only way to go if you really want to get that performance that you require. So from the answers, I see that many people do not have experience with GAN. There are some who do, which also expected at Power Electronics. So there are some other talks also focusing on GAN. So I think that about a fifth of the people has actually designed and sold a product with GAN. So that's already quite a lot for a new technology. So we saw 4 main challenges in working with GAN, and I know that that some challenges have already been spoken about by others, or will some talks will go in depth on that. So I would like to focus on one of these 4. But before that, I will explain a bit about our design. So our motor controller consists of a motherboard, so that does all the control, the filter end control, does the sensing, and sends the signals towards the power stages. And those power stages contain the actual switching devices, so the gallium nitride FETs. And those power stages are glued to an aluminum base plate, which is then screwed to a heatsink. And that's the whole stack, which you can also see in this picture of the realized motor controller. And because we have such high current requirements but low nominal power requirements, we have many FETs in parallel. So that was one of the challenges we had to face. This, of course, is related to the layout as well. Many people might already know that that layout with GAN is quite a challenge, but doing it right might result in great results. Cooling is a challenge. The components are necessarily quite small, which is also something we found out, that cooling is a difficult challenge when using GAN. Such a high power density is difficult to cool, especially when you have to also have to really look at the layout for signal integrity. This all comes together in the design of the gate driving. This is something I wanted to talk a bit about a bit more. So our challenge was to have a half-bridge driver which could handle 165 volts. So a 3-phase motor controller is in the basis is a system with 3 half-bridges, which are controlled to create the currents for the 3 phases of the motor. So we have a bottom FET and a top FET, but the top FET, the gate signal is referenced to the switching node, so one of the 3 outputs of the motor controller. So compared to the ground of the motor controller, high voltages will be seen there. So we needed a gate driver that could keep the gate voltages of the components within the tolerance specified by the datasheet. And the type of these devices we used could only go up to gate voltages of about 7 volts, which is lower than most silicon MOSFETs. That was quite a strict requirement, but the optimal driving voltage was also more than 5 volts. So it's a very, very small margin. But we needed a driver that could handle that, and even up to voltage of 165 volts. So when we started, a gate driver wasn't available. I know some are now. But again, we then had to use an isolated driver for the high sides. And there might be other reasons why not picking an integrated half-bridge driver is for your solution. For example, the speeds, you want more control over the speeds, or the single driver has better performance than the half-bridge driver in total. It really depends on what is available. And in our case, the half-bridge driver wasn't even available. So we had an isolated driver, but then using many FETs in parallel was one of the challenges we faced. Because all the FETs have to be driven. So what we came up with is a single isolated world, but we used a single driver per FET. This is really the advantage of working with the solar team and having the resources to design something like this. Because in many normal applications, a single driver per FET would be quite expensive. It still is, but for the solar team, it was acceptable because we only made a couple of motor controllers in total. And we used a single isolator. In this case, we, as you can see in the picture, we have a FET with a gate driver very close, so we could keep the gate loop very small. That is because during switching, all the main current will go through the source of the device. And that has some small inductance. And at the switching speeds of GAN, which is in the order of a couple of nanoseconds, we can actually create quite a voltage drop over these connections. So one of the solutions the device we chose had was to have a source sense pin, which is used in more devices. So you can actually connect the return of the driver to a separate pin to make sure that the main current doesn't go through there and creates that voltage drop. Only the problem was that if we use a single isolator, we had to create a large plane for this gate return path. So that main current goes to the source. That's something we want, but it didn't want that voltage drop. So we eventually decided to create a short circuit between the source sense and the source. For our application, this showed good results. So we're happy that worked out. It even decreased the inductance of the total source a bit, so that was a nice bonus as well. So we have individual drivers per FET with an isolator further away. So we even eventually chose for introducing another isolated world in the bottom FET. Normally also maybe a bit of a weird choice, introducing extra components. But because we only have a couple of devices and we all measure them by hand, and everything is checked by hand for this application. It takes quite a lot of time. We actually really have precise timing at the moment. There's not a lot of spread between components in terms of timing, but the maximum values can differ quite a lot. And by all measuring that over the application, we found out that we had quite a strict timing, and we could use that to decrease the dead time in the end. So that's one of the reasons why we also chose to isolate the low side. Another thing was robustness, having a separate path for the ground currents. In this case, seemed like a good choice. I have a question mark after robustness because introducing extra components, of course, could also decrease the reliability. But then measuring everything by hand still is quite an advantage. So in the end, we realized a motor controller using GAN. It was bench tested on the motor test bench by the team. We also gave it to them so they could drive around in a mock-up vehicle, which you can see in this picture. It's not the actual vehicle, but an aluminum frame containing all the mechanical and electrical components. And it showed very good results. So it was about the efficiency we expected, and we could really drive around. First days were quite fun. We had a driver in the mock-up, and we're also still working on improving our Viper building block. So working on the control of the motor. Of course, for this, integrating it in this vehicle, we still had to make some tweaks, and we could do that on the spot at the testing facility. So that's a bit about the solar team and their Gallium-Nitride motor controller. And I have some small details left, which are not very related to the rest of the story, might be interesting to some people. So I'm first very interested if there are some questions from the audience. So, for the people that have done something with GAN, do you have some questions? People that want to use GAN?
We have a question coming in. Okay. From Maurice Gielen. What about application of the developed motor and power control technologies in the EV industry? Can you elaborate on that?
Yeah, so I expect that the future will go towards faster switching components. So gallium nitride is the fastest. I don't know of any electric vehicle applications with GAN yet, but I do see that it's coming. So one of the reasons for us to go into this project is to learn a lot about GAN while it's still in development. Get a feel for it. It didn't go all smoothly. So we have a working motor controller, but we also had some problems. Might elaborate a bit about it later. But you learn a lot about that, which makes us ready for using GAN in some of our products for customers. And I also think that the electric vehicle industry will eventually go to something like GAN because it's much more efficient. You can make more efficient systems. And that creates more range for electric vehicles.
Okay. Let's see if there are more questions coming in. Maybe in the meanwhile, you can a little bit elaborate about the Solar Team Twente. This year, they will not go to Australia, unfortunately.
The team is still quite busy building the next car. So also quite busy upgrading our motor control. But they have found an alternative race in Morocco. So the race usually is in in Australia, but due to the COVID restrictions, that couldn't go to plan this year. So the alternative is in Morocco. It's a different race. It's quite new, but already some teams have signed up, and we expect them to race at the end of October.
Okay, good. I see there is a question coming in from Paul Rebers, if I pronounce it correctly. What is the switching frequency, is his question.
Yeah, so that's something we saw as one of the factors to optimize. It's actually quite low. So it's somewhere around 10, 20 kilohertz. That really depends on the rest of the system, as I explained. So normally you choose GAN so that you can go up to higher switching frequencies to make everything smaller. In a solar car, size isn't that important in the components. It is because it has to fit, but weight and efficiency are much more important. So we actually can change the switching frequency to see what is the most optimal, combining all the other components, which are also still in development, which are being improved at the moment.
Okay. Then we have a question from Jeroen van Duivenbode. The trend in electronic vehicles seems to be higher voltages to reduce currents and copper loss. What are your considerations to limit the voltage to about 150 volts?
Yeah, that's really driven by the team. So they have multiple challenges besides the optimization of the drivetrain. They also have a solar panel which outputs a certain voltage, which can be taken into account, but they also are a race team, and they have to make sure that they, if something goes wrong, they have backups. And so in the very first edition of the new motor controller, we had to make sure that we still had a suitable backup during the race. So their voltage is one of the last things to change when everything else has changed. But yeah, I think that going to higher voltages would make it possible to increase the efficiency even further. But for the team, that wasn't a possibility at this time.
Okay. Maybe there's time for one more question. So if there is somebody that still would like to ask Jan a question about the Solar Team Twente, or maybe something about 3T, that can also be done. And please post your question in the chat.
Yeah, if there are not more questions, I can elaborate a bit about one of the fault conditions we saw, just something we learned, which also might be interesting to the audience. It's not very related to the rest of the story, but something that might be interesting to some people.
Maybe we have a quick question coming in. I see from Henk Huisman. Do you have any issues with magnetic components?
Well, we're still the components are being improved, designed. So the main challenges are in the development. I don't know of any issues in practice. But yeah, it's difficult to improve a lot. So there are very small gains in the magnetic components mostly.
Okay.
There's some extra comments. See?
Yeah, it's also from Hank some additional comments to the question that he posted, but I think you elaborated about that quite well.
Yeah, so it's the rest of the question is due to the steep flanks of the PWM voltage. So it's true that GAN switches quite fast. So that creates high transients. So we have some extra filtering in there to make sure that for the components the transients aren't that extreme. But yeah, that's one of the challenges with GAN. You want to have as fast a switching as possible, but you also want to limit the flank to not create trouble in the rest of the system.
Okay. I see no more new questions appearing, so maybe you can elaborate a little bit about the test results.
Some interesting things about the devices we used. Eventually, the wisdom is just to keep within the limits. But yeah, of course, we had some failures during the development process, and I want to elaborate one of them. It could be unique for this type of FET. But maybe it will inspire some people to also look at their problems a bit differently. So we gave the working motor controller to the solar team, and they started testing with it quite a lot. During the test period, they usually drive at a short stretch of road, So they have to turn quite a lot. And as I explained, the nominal power is quite low, but the maximum power of the controller is very high, which they also used to accelerate quite fast. It's not necessary during the race, but during testing it was handy to be able to turn around quite fast. Eventually we got one of the controllers back with an undervoltage error. That was the first symptom. And it turned out that the gate of one of the devices, the switching devices, was shorted to its source. So we did some testing, thought we had some electrical problems, although we measured everything and everything seemed to stay around that 5-volt gate drive voltage. It's not going over the maximum datasheet values. Still, we had those problems. Although after testing, suddenly the device worked again. And we could drive around again, so the short had disappeared. So not satisfied with not knowing what the problem was, we together with another company we looked inside of the device. So stripping it apart layer by layer, we looked at the problem and quickly found out that there were some small air bubbles within the package. So while the GAN die was still intact, turned out that the team had been pushing the motor controller a little bit too much, making it heat up too much, and the components probably started degrading due to the temperatures. Eventually, one of the air bubbles started to appear right at the dividing line between the gate and the source. And that's also where the short happened. It was a very small, fine grain probably, which could be burned away with a couple tens of milliamps. So another solution would be to use a very strong gate driver, which just could burn through those small shorts. But of course, the real solution was just to tell the team not to push the motor controller as far anymore. And then the motor controller has been used during a race and several more testing days. So I thought that could be interesting to some people. Might be device specific, might be something related to something you're experiencing. If you really go in depth, you eventually can solve it. So we successfully realized a motor controller with GAN. So I don't know if there are any more questions.
There are two more questions that came in during the last slide. One from Chitte van der Ploeg. Did you apply EMC filters?
So yes, there's a bit of EMC filtering on there.
Okay.
So due to the fast switching speed.
Yep. And then the final question is from Hans Welschen. How did you monitor the working of the FETs in parallel?
Yeah, so we looked at the group in total. So we do not monitor individual devices. We look at the driving voltages, and that way we could eventually find the phase in which the problem occurred, and then manually find the actual problem.
Okay. I think that were the questions for today.
All right. So to conclude the presentation, this of course was a one-off product. 3T really supported the solar team in the development, but it's a product they intend to use. They have already used. But many of the solutions we found, and we also thought that the team members could also be used in applications in silicon or even silicon carbide power electronics. GAN has some more advantages next to the efficiency, so we really used it to get a more efficient system. But using these devices, you can also create much more precision by switching faster. One of the products we use it in is our Pepper building block. So it's a very, very high precision power amplifier. But you can also use it to decrease the size of your products. What we really found is that GAN is very useful for the more challenging applications at this stage. But we also see that it's becoming much more integrated and really much more easier to use due to the several components that come into existence. Okay, well that was my presentation about the gallium-nitride motor controller of the solar team. Thank you for your attention.
Yeah. You mentioned in the presentation some building blocks from 3T, the Viper and the Pepper. For those who are interested in that, they can turn to the 3T website and look under the menu solutions. There you will find a description of these building blocks, so you can have a look at that. And if you would like to have a quick talk or chat with Jan or Bert van den Berg, our technology manager within the company, then drop us an email at info@3t.nl, and we'll make sure that it will get answered. Okay.
Right.
Switch positions. Yeah, also from our side, thank you very much, Jan. Thank you, Richard, for the presentation. We will share the presentation also afterwards in the replay version. If you fill in the evaluation form, that will pop up any minute. We will ask you to let us know how you like the event. You can also do it later, of course, when you follow more sessions. But if you is this the only session you followed, or maybe followed earlier session, please fill in this evaluation form so we can continuously improve our event. This is the last session of this morning. We have now a lunch break till 1 o'clock, and after that we have a session of Antonio from PureDuke on behalf of Telerex, and the subject of the presentation is ultra-wide input DC-DC simplifies designing. You can still register for this session or other sessions we have today and tomorrow via the Power Electronics website. So thank you very much for your attention. Thank you very much, 3T, for coming to the studio and for this interesting presentation. And what Richard and Jan also mentioned, if you have questions, contact 3T directly. Contact details are behind us and also will be shared, of course, in the replay. So thank you very much for your attention. Have a good lunch at this moment, and see you later in the program. Thank you very much.